the recording though. All right, so today, and let's go ahead and see what I'm capturing here, because I asked for somebody else to ask for a videographer, and let's see if I can. They will be the quiz would be on a computer or on a phone. Do you have a cell phone? What? Do you have a cell phone? A smartphone. Do you have a smartphone? Yeah. Yeah, you can take it on there. How? It will be on Canvas. If you need it, it'll be on Canvas. All right. So actually, yeah, we need since I don't have a videographer, I guess I'll do it this way. Okay. So yeah. Well, at least you're spared from my terrible handwriting, so there's that. So today we're going to learn about data types. Okay? Class. So select folder. Sorry, give me just 1 second. So boom. Come on. Window. Perspective, reset perspective. Okay. And I'll need the chair for today. Okay. Not exactly the most ergonomic of, things, but we'll go ahead and start by learning about data types today. So package, data types, and new class. Learning about data types. Okay, so today, as you might guess, we're learning about data types. So today we're going to be learning about data types, and as you might guess, that's infers learning about data. And really, your computer only knows about like one kind of data, and that's a number, right? So everything in your computer at its core is stored in a bunch of electrical signals, which are translated as zeros and ones. So don't think about it as electricity. We abstract it away and think about it as zeros and ones. Okay? So basically, all data in a computer is stored in what we call binary. And I've got a great write-up I'll post about a binary. Now, because I had to teach a class where I had to explicitly teach about binary and how to convert decimal numbers into binary, we don't do that in this class, but it's a useful enough exercise to learn how how binary numbers work that we're going to take some time and do it right now. Okay? It's not anything that you'll really be subjected to too much on an exam or anything, but it's useful to know because I'll be referencing back to it as though you understand how to do it anyway. So binary numbers get their name because you only have basically two choices for a digit. Now in our standard math, using Arabic numerals, we've got 10 possible choices for a digit, which I can just simply make appear on screen by just swinging my hand across the keyboard, which is nice. So, right, these are the 10 different digits you can have, right? Any possible digit can have these choices. So as a result, I've got basically this number, 458, right? That's, there's 10 possible choices for a digit over here, 0 through 9, although, again, starting with 0 looks a bit weird, right, for 3-digit numbers, but just bear with me on that. So there's 10 possible choices there, there's 10 possible choices here, and there are 10 possible choices here, right? And what this translates down to, when we get right down to it, is that we're saying that this number, 438, is equal to 4 times 100. So we have 4 hundreds, right? And we have 5 tens, right? And we have 8 ones. And because it's a decimal system, basically, we can actually, extrapolate this. So say I wanted to make this let me just go ahead and add something over here, and I'll put commas just for our usefulness. So here, we add it. If we add on to this, that also means we have 0 1,000s, right? And 1 10,000. Okay. So we're going to be if you can't get, if you aren't, so if this is boring, then that's because you're just going to be relearning a lot of basic math today. But it's kind of essential for understanding how how data is going to be used, and then how we're going to evaluate it in computers. So we've got 1 times 10,000, 0 times 1,000, plus 4 times 100. And we can simplify this actually a bit, or we can generalize this by basically saying that since this is the 10th place, this is 10 to the 0th power. Sorry, 1's place is 10 to the 0th power. 10th place is 10 to the 1st power. 10 to the 100th power. Sorry, not 10 to the 100th. 10 to the 2nd power, 10 to the 3rd power, and 10 to the 4th power, right? Let me go ahead and just show you. So, like, I'll just keep this. I'm not changing any of the numbers here, for, in actuality. Wait, sorry. I'm not actually changing any of the numbers here. I am just changing, how they're represented, right? So 4 times the hundreds place, 10 to the thousands place, right? And in the 10,000s place, right? Now this breakdown is how it works in binary. And it's actually a lot simpler than it works out, than it looks. So binary numbers, they look something like this. They're a bunch of 1s and 0s. You only have 2 choices, 1s and 0s, okay? For a binary number. So let's start by counting. This is 0 in binary, right? This is 1. Okay? We've expended all the places we can represent with a single digit. Okay? Can't represent too many numbers with a single digit. A single binary digit, by the way, is called, we contract that and we call it a bit. Bit is just simply what we call a binary digit. Okay? So we need another binary digit, another bit, if we want to store information. So this is still 1, right? But now, this is 2. This is 3. And now we've expended all the amount of space we have because, again, 2 bits doesn't store that much. This is 4 as a result. Okay? So how's this working? If I've got some string of digits like this, how do I know what number it is if it's in binary? Well, it's kind of the same thing. A thing of how this works. So this is over here, the 1's place over here. The 2's place is over here. Notice it's the 2's place. Sorry, insert. Oh, pressing the wrong key to do that. Okay, 1's place, the 2's place. So notice that this is the 2's place, not the 10's place. The 4's place. This is the 4's place, and this is the 8's place. So what's going on here? Well, the first digit is 2 to the 0th power, just like the first digit over here was 10 to the 0th power, right? Second place over here is 2 to the 1st power. Just like over here, it's 10 to the 1st power. 2 to the 3rd power, just like we have 10 to the 3rd power. Or 10 to the 2nd power. Right? 2 to the 2nd power. Obviously off my ball today. 2 to the 2nd power, 10 to the 2nd power. 8 to the 3rd power, 10 to the 3rd power, right? So, so this is, oh, come on. Here we go. So, 3, 2, 1, 0 in terms of what the power is. Okay, so we're dealing with powers of 2. So this means that this number is equal to, well, this is the 8th place, so this would be 1 times 2 to the 3rd power, which is 8, plus 0 times 2 to the 2nd power, plus 1 times 2 plus 1. times 1. 2 to the 0th power, which this becomes 1. 2 to the first power becomes 2. This is 4. And this is 8. So doing this in binary comes down to 8 plus 2, which is 10, plus 1, which is 11. So that was a lot of work to do this, but it's not actually too hard. And representing binary numbers is a bit, there's a bunch of tricks, but this is essentially it. Like we have to answer some questions later about how in the world do we represent negative numbers. But, that's not something that I need to cover in that class, but I'll, briefly go over it. But this is what's stored in your computer, ones and zeros. And all we're doing is we're tricking this piece of silicon into thinking by making it manipulate a bunch of zeros and ones. That's all we're doing. And these sequences of ones and zeros, individual ones and zeros are called bits. And the unit that computers most use are that it can manipulate at all at once. Your computer doesn't manipulate single bits. What it does is it manipulates bytes of data. A byte is a group of 8 bits. So it is basically this sequence of numbers over here. 0, 0, 0, 0. So basically any combination of these guys. Now this can represent, this is 0. So the biggest number that can be represented by this is 1111, 1111, which is, that sounds a bit intimidating, but it's around 255. So we can represent any number from 0 to 255, which seems like a bit underwhelming for such a long number, right? All right, so let's talk about how do we actually store numbers. Now, because this process is actually invisible to us, but this is why basically that, we're going to be dealing with, some weird values later, and some things are going to crop up later that don't make sense because you're thinking in decimal, but your computer's thinking in binary. Okay? So let's get started. Your computer can hold certain types of data. Right now we're going to learn how to use our computer as a really over-glorified calculator today, which will enable you, how many of you are in physics this semester? Awesome. So you'll be able to do your physics homework by writing programs. So we need to be able to store numbers. Now, we deal with 2 types of numbers, 2 different classes of numbers in basically when we're dealing with stuff. We deal with what we consider mentally easy numbers and mentally hard numbers. The easy numbers are what we call integers, right? Because they don't, and those are whole numbers. So integers are numbers like this, system.out.println, and I'm not going to be throwing them into a string because your computer deals with numbers just fine. Integers are numbers like this, just nice big numbers. Just nice whole numbers, right? Run it. It's just printing that out. Another integer, also integers can be negative, right? So you can deal with negative integers, right? So those are what we call and if we want to store them in our computer, we just store them in what we call an int. An int is short for integer because integer is a long word, and we don't like typing long words if we don't have to. So int is just short for integer, and we can basically create what's called a variable. So int x is equal to 5. And this is going to work very much the way you think it should, which is that we are going to take this value on the right, 5, and we are going to store it in x. Okay? I don't know why it decided I needed to know more about the system class, system.out.println x. So we print out 5 here. Okay, right? We asked it. So what happened here? So this equal sign leads to some confusion sometimes. Okay, because in mathematics we talk about hey, this value is equal to this value. So we say that 5. In math you might see something like this. 5 is equal to 2x plus 1 solve for x. You might see that in math class or something. That's not, and the equal sign simply says that this side and this side balance out. That's not what the equal sign means or the equals symbol, I should say, means in computer science. That's not what's going on here. Okay, what's going on here is that this equal sign is actually what we call the assignment operator, where what's going on, so this is assignment, not equality. We're taking what's on the right and we're storing it on the left. It's easier if you think of it as an arrow, like this. We're taking 5 and we're storing it in here. Now, why don't we just use an arrow if that's what we mean? Well, because we would want to translate this if we were doing math as less than negative negative, which is kind of weird. So less than negative negative 5, which would be less than 5. So int x is, so that doesn't work. What about this? Why don't we use this for an arrow? Well, that we would read that as less than or equal to. So we can't really use that. So in some programming language, they were like, okay, so for assignment operator, we'll just make it look like this little weird thing instead, colon equals. And there's still that use in modern programming language. Like Go has a special use for that, where it does a type inference. But this one is, but as you can imagine, since we just eventually just shorten it to the equal sign because we're lazy, and it kind of means we're saying that x is equal to this value. We are taking 5 and we're storing it in x, right? So we're taking the value on the right, we figure out, and the thing on the right could be something really big and really weird, and we're going to store it on the left. So right now I'm going to talk about like how Java works with integers. So as you can imagine, it works like exactly you would if for almost everything it works exactly as you expect. Right? X is equal to 5. It figures, we asked it to print out x times 2. So it figures out what x is. It looks it up and says, what did we put down for x? Oh yeah, it was 5. We're gonna multiply it by 2, so we get 10. Okay? Let's see, what else can we do with these? Well, we can just do kind of any mathematical expression we would like. So x times 2 plus 1. Now, it's going to go, so it will do, and that's going to give us 11. Okay? Now, here's a good question. Because, and you really have no way of saying what's right or wrong for this. What would 1 plus x times 2 be? Should it be 12 or 11? Right? Now, what if we're working across, now obviously because we're computer scientists and we're coming out of math, and programmers who are coming out of math, we'd really like it if we, if this works the way that mathematicians think it should work. So it works exactly according to the rules of PEMDAS, right? Everybody remember, please excuse my dear Aunt Sally? If you grew up in American school, it was different stuff because, they use brackets. I think PEMDAS in like Commonwealth nations, but it's order of operations. First we evaluate our parentheses, then our exponents, then our, which doesn't actually have an operator in Java. Instead, we use something else. Multiplication, division, add, and subtract. Okay. So we can do anything we want over here. So 1 plus x. So this is going to do, so here we're going to do 5 times 2, right, first, which gives us 10. So then it's going to be 1 plus 10, which is 11, minus 4, which will be 7. Okay, so this is all according to order of operation. Okay, if I want things to be changed up in a certain way, if I want to ensure that order of operation goes in a specific way, I just throw parentheses around everything. So this would be x times negative 2 plus 1. So 5 times negative 2 plus 1, so negative 9. Right? This is easy stuff, right? This is 4th grade math that you had to deal with, and you've been basically, so this is old hat. Nothing too exciting here. All right, so why am I going over to this, wasting time on this if it's not any different? Well, the answer is because it is a bit different in some regards. Because division operates like at a 4th and 5th grade level, let's say. Okay, so let's do, let's see. Let's do x divided by 2. So x is divided by 2. So 5 divided by 2, right? So if you were given that as a problem, you'd say 2.5, right? Because we know about fractions, and and decimal points. But again, your integer for when we're dealing with integers and the expression. Remember, this is what we call an expression, right? So this evaluates into something. An expression is just a bunch of symbols, just and operators just glommed together. So this expression, right, is going to be evaluated at a 5th grade level. And in 5th grade, we don't know how to do fractions. Or in 4th grade, we don't know how to do fractions. So when we're in 5th grade, we would say like 5 divided by 2 gives us what? 2 remainder 1, right? So we run this, and 5 divided by 2 gives us 2. Now, so the one way to think of this is that it's just operating at that 4th grade level where it doesn't know how to do fractions. And the other thing is, well, it's integers, so it doesn't know about fractions anyway. So when we divide by integers, we're asking how many times can we subtract 2 from 5 and get an even result, and not go below 0. And the answer is 2. We can do it 2 times. We can subtract 2 twice from 10. This 2 goes into 5 twice. All right. So I just mentioned we're doing it at the 5th grade level, though. 4th or 5th grade level. If we get the quotient, is there a way to get the remainder? And there is, with the percentage sign. This is not the percentage sign, though. This is a special symbol called the and it's got a very funny name called the Modulo Operator. And modulo is a bit of a mouthful, so we just shorten it to mod. Okay. So we say x mod, we are saying 5 mod 2. And this is asking, what is the remainder after we divide 5 by 2? And the answer to that is 1, right? It divides evenly, and what's left over is 2. That makes sense to everybody so far? So this modulo operator is a new operator, and it's weird and it's scary, I'm sure, but it's not too bad. Okay, so let's go ahead and do a bunch of system.out.println. So x divided by 2 system.out. So here we've got our 5 divided by 2 and our 5 mod 2. Let's go ahead and do some more. So let's go ahead and see 10 divided by 2, 10 mod 2, and 10 divided by 3, and 10 mod 3. Okay, so 5 divided by 2 is 2. 5 mod 2, the remainder after dividing 5 by 2 is 1. 5 divided by 10 divided by 2 is 5, right? And if we divide 10 by 2, we don't get a remainder. So 10 mod 2 is 0. 10 divided by 3, that goes into it 3 times, right? So we're basically, when we divide by, an easy way to think about it is that when we're dividing integer by another integer, if we have any, leftover bits, like a decimal bit that comes after, our floating point, we just throw that out. So, 10 divided by 3 is normally 3.33333 repeating, and we're just going to throw out that repeating 3. Okay, 10 mod 3, which is what is the remainder after 10 divided by 3, is, that's 1, because that's what's left over. Now, there's a lot of others. Now, modulo actually has, very powerful mathematical meanings, and it's very important and those meanings make it very important in cryptography. But for right now, you can just think of it as, I'm going to lie to you and say it's the remainder operation, right? So if you think about it as the remainder operation, it actually just, that's pretty much where you need to be in terms of thinking about it. It's not too far from the truth. It gives you the remainder after, there. And it exists in the same space as multiply and divides in terms of order operation, because it's kind of a division operation, right? So if I say system.out.println, and let's just make something up off the top of my head. So 10 mod, so let's say 10 divided by 2 times 100, right? That will give me you know, 10 divided by 2, which is 5, times 100, which is 500. If I do, let's see, and if I mod this, right, it's on the same level, so it's going to go left to right, where 10 divided by 2, sorry, 10 mod 2 is 0 times 100, which is 0. Okay, so mod occurs at the same exact, you know, level of stuff. It does, it go in terms of, if you've got a bunch of multiplication and division operations and modulo operations, you just simply evaluate it left to right, like you would anything else. Okay. All right. Since we're doing integer division, there is one thing to know, one big thing to know about though, which will throw you for a bit of a loop. And spoiler is crucial for you to figuring out the problem with one of the problems on your second homework, which is what happens if I do this? 5 divided by 100, right? What's that quotient? Well, that's also 0, right? Because 100 goes into 5 0 times, right? So when you've got integers, this number is really easy to figure out. So here's a free point on your examination, on your first exam, by the way. So I always put something like this on your first exam. So something like 5 times, so 1/2. So I'll put something like this on your first exam, like guaranteed. Well, just bang on the keyboard, and it's going to be something like 1 divided by 2 times some big number, right? That you don't have a calculator for. How in the world do you solve this? And ask, what does this evaluate to in Java? Well, 1 divided by 2 in Java is what? 0. And 0 multiplied by any big number is, yep. So similarly, the other variation I love about that, I love to do is something like this, which is 5 divided by 4, right? Times this really big number, right? So 5 divided by 4 is 1. So 1 times some really big number is I just have to copy that really big number over into the space for the answers, right? So you'll find that in physics and in math, we really like to, you know, work with zeros, ones, and twos and make you multiply stuff by those amounts because it's really easy to, because it's very easy to simplify that kind of stuff out. So let's see. What else? So those are integers, right? Now, how big can we store them? So how big, I mean, is there a limit to how big my numbers can be, right? So in math, like in mathematics class, the answer is a definite no. You know, I can have, you know, I need a bigger number, just add 1 to the one I currently have, right? Okay, so, you know, how big can my numbers be in you know, Java? Okay, give me an error here, and it says that that's out of range for the type of integer. So that's 1, 2, 3, 4, 5, 6. So that's 100,000. So that's 3 billion. So okay, let's dump it. Drop it down to 2 billion. Nope, still a bit too big. 2 billion a bit. So the limit is somewhere above 2 billion. Now, why is that? Well, because integers, ints, are what we call 32-bit numbers, which means that when we create an int, and all basically integer numbers are ints by default, okay, that means that essentially that we can have a range of 32 bits. Now, mind you, we also have to use negative numbers there. So that means that one of the bits is going to be used as the positive or negative sign. So we will have a 0 if it's a positive number, sorry, if it's a positive number, and a 1 if it's a negative number. And the rest of 31 bits are used for that. So the biggest number you can have is basically 0 and a bunch of 1s after it. So rather than trying to calculate that ourselves, let's go ahead and ask the computer what that is. So integer dot, so you don't have to remember what this is, but it's something that exists in your computer, and you can ask, what is the biggest value that an integer has? What's the biggest value you can store in an int? And it's somewhere over 2.1 billion, right? So it's 2,147,483,647. And for most applications, that's a plenty big number because billion is really big. But interestingly enough, that's not bigger than, you know, the number of people on Earth, right? So we need some. So and it seems like maybe we'd like a computer system to maybe keep track. In fact, there's a system online that estimates the number of people on Earth. So it's obviously not using a 32-bit integer. Okay, sometimes, though, we need bigger numbers. So you're not going to use this too much, but you do have something called a long. Okay, and longs work exactly the same as integers, only they use 64 bits, right? Let's see. Don't tell me that's out of value for a long. I have to put L on the end. I didn't want to show you that, but whatever. Some long value. Whatever. I'll just say 0 for right now. This is a 64-bit number. Right? It's pretty... So these things can actually be... so this isn't... It doesn't hold twice as much. It has twice as many bits. Right? So we're talking... 1 bit used for positive and negative still, and then we have 63 bits as opposed to 32 bits, which really makes this a really big number. Okay, so the maximum value you can hold in a long is, let's see, hundreds, thousands, millions, billions, trillions, quadrillions. What comes after quadrillion? Heptillion? Sure, let's go with that. Point is that's big enough that we don't know it off the top of our heads. Okay? That's how big these are. That's plenty big for our applications, right? For longs. As you might, so longs we will use if we have to, but we're pretty much but I don't really remember ever having to need them during the semester, right? Normally we don't go above numbers that are above or below positive 2 billion because the range is almost exactly the same in the negative. Okay? And you might imagine, well, if there's a long integer, is there a short integer? Yeah, we pretty much never use this thing. It does exist, though. It never, if we really care about how much memory we're using, we can use a short to represent a 16-bit number, right? But that's pretty much never going to come up. It's probably not even going to come up as an extra credit question, so that thing never comes up. All right, but those are integer values. And as we know, if you're dealing with science and stuff, we're using stuff that, isn't just whole integers. Like in physics, we have to deal with a lot of time with these annoying, decimal numbers. Sorry, floating point numbers, as they're called. Which means that, they have a floating point in them. So these numbers. If we even want to figure out, what the perimeter of a circle is, we'll need to know what the value of pi, which is, 3.1415 and some change, right? So the computer needs a way of storing these numbers, too, if we want to store them in variables. And I'll get into how we use variables a bit more as we continue in the lecture. But first, we have to just talk about our data types, right? So obviously, we can handle numbers like 3.1415. So now these numbers are what we are these are floating point numbers. And for a reason which is non-obvious to you, we call them doubles. So this is what we call a double. Now, why is that? Well, because just like we have 32-bit integer numbers, so let's go ahead and correct this, 32-bit integers and 64-bit integers, right? We have 32-bit floating points called floats. And if you were working in C, this is the default type, I think. So float f is equal to 3.1415. Okay? 32-bit floating point. Okay. Now, it's saying that it's giving me an error because the default type in Java isn't a float. And if I want it to be treated as a float and say this is a floating point number, I'd put an F underneath it. But the default type in Java isn't a floating point number. Instead, it isn't the 32-bit number. It's the 64-bit floating point number, which is double the length. So we call it a double. Double D is equal to 3.1415. And this is a 64-bit floating point number. And these have a really weird configuration, but these are essentially just binary decimal numbers that are being stored. So, and these work, now there are no sorry, these things work exactly the way you think they would. Yes?
So what does like double do?
Double is just it's the name of the type, right? So we use it for floating point numbers. Double just means double the length of a float, just like long is twice as long. So, now these double numbers work exactly how you think they would. So if I wanted to figure out like, so let's go ahead and start by saying some stuff. Like, so let's go and actually deal with, write something pretty basic. Like super basic. Like calculating the radius of a circle. All right, double radius. Let's go ahead and figure out, say our radius is, maybe 145.5. That's the radius of our circle, okay? Double pi, right, because we need that for our circle, right? We need to know what, that's equal to, let's say, 3.1415. Although if I want a more exact value, Java does know a more exact value for pi, but this works for us right now, okay? And radius and pi is pretty much all we need if we want to say what the radius is. So print line, let's see. Let's go ahead and print out the area of the circle, which is pi r squared, right? So that would be pi times radius times radius. Okay. And that gives us the value of 66,500 and change, okay? And so the cool thing about using variables here is that I didn't really need to. I could have just copied, I could have done this, right? But by using a variable here, okay, say I want to test a different radius, right? Say I want to test a different radius. If I want to test a different radius, I have to change two values, right? I'd have to change this. If I want to change this to 100.5, I'd have to change them. I'd have to change two numbers. Here, I only have to change one number, which is the radius over here. So variables basically allow me to really change my code really quickly like that. So now 100.5, that gives me, 31,700 and change. Okay. So that's pretty cool, but it doesn't really present meaningful information to the user. So I could do something like this. One solution is system.out.println. Sorry, print, right? Because I don't want. Sorry, let's go with print line first. Circle is right, and it will print out some text before I print out that stuff. So the radius of the circle is 31,729. Okay? But it's on different lines. Why don't we try to get them on the same line? So, right, I could do, in that case, print, right? Because print means, if I do print instead of print line, it doesn't come up with a end of line character. So just put a space there. So now, the radius of the circle is that. But it'd be really useful if I could just, put this all on the same line, and you can. So first, we're going to learn that the plus operator does a bit more than just doing addition. Okay. That's kind of weird. The radius of the circle is this. All right. So this is our first lesson in automatic type conversion. Our first lesson in automatic type conversion. Okay. And what's going on here? Well, we need to evaluate this kind of stuff. So this is an expression, like anything else. This needs to be evaluated by Java in order for us to understand what it is. Okay? So the radius of this circle is, plus pi. So we've got this this bunch of characters, which is called a string, by the way, plus pi times radius times radius. Okay. And what's going to happen over here? We've got, what we're going to do is that we're going to calculate the numerical value. And then what happens is that we glue it to the string, to this string over here, all this text. So that's how that kind of addition works. Now we'll learn about strings in a bit, but this is how doubles work for the most part. The other interesting thing to note about doubles is that, because we're on the topic of automatically converting stuff, is that you can store integers in doubles, right? You can take this integer and say, hey, take this integer and store it in this double radius. I want a circle of radius 100. And it'll go no problem. Because, of course, doubles can store really big numbers. Why? Because it's going to be storing it in scientific notation in the computer. Let's go ahead and see what the biggest value we can store with a double is. It's going to kind of be actually quite astonishing. Double dot max value. So this is the biggest thing you can store in a double. All right, that's 1.79 and change times 10, right? This is scientific notation here, times 10 to the 308th power. That's the biggest number we can store in a double. That's pretty massive, right? That's a huge number. I mean, in min value, you know. So 4.9 times 10 to the negative 324th power, which is about as small a positive number as we can store. This thing gets pretty small. So we can store these numbers we can store quite a number of numbers in here. So it makes sense that we could easily encode a number like this into scientific notation and then store it in a double. So whenever an integer and a double meet, the integer converts into a double. It converts into this. The integer automatically converts into this. Yes?
Does the operating system have an impact on the differentiation of double?
I think no. In Java, no. All doubles are 64-bit numbers in Java. That matters in C, right? In C, that matters. But in Java, because they're all running on the Java virtual machine, all of the numbers, all ints are 32 bits, all longs are 64, all doubles are 64 bits. Okay? So that's pretty cool. So let's show another example of that. System.out.println. Let's go ahead and show another example of this. We've got 1 plus 1.5, right? That'll give us 2.5. And what happens is that the 1 over here gets converted into 1.0, and then it gets added to 1.5. 1.0 plus 1.5 is 2.5. Pretty easy math there. I'm not going to do any really challenging math here. Okay? So whenever doubles and meet an integer, they have to convert. So that means we can represent 1 over 2 if we're clever about it, which is that we can do 2.0, right? If an integer and a double meet, the integer converts up to a double. So now we get 0.5, right? And it works the other way around. If we do 1.0 divided by 2, the 2 converts into a 2.0, right? So anytime integers and doubles meet, they convert. The integer converts into a double. And that's just simply because the doubles can represent way more values. Okay? Now, there is a bit of a quirk, though, with doubles. So I'm going to go ahead and... I need to see. So this is probably going to crash. Sorry, yeah, that goes over to here. So I need to just change this away to here for just a second and see. This keeping? Sure. All right, everybody know what happens when we do this, like 1 divided by 3 in a calculator, you get a bunch of 3s, right? Repeating. And this is because the decimal system can't properly encode 1 over 3, right? It doesn't have a way of basically saying 1 over 3 without giving us a bunch of repeating integers, right? This is better, when we do 2 over 3, that's better represented, where it basically says, the best I can do for 2/3 is a bunch of 6s, and then I round up the last one, right? And this is because we can't represent 2 over 3 perfectly electronically. There's just not enough space for an infinite number of 6s, right? And also, it just doesn't display like 2 over 3. It's just not the way we've programmed our calculators to work. Okay, so let's see. Does it switch back to screen and camera? Sure. Awesome. I don't need to boot up another Eclipse instance. Terminate. Cancel. 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 All right. So similarly, Java has some similar problem for some of these numbers. Why is it? There we go. Okay. So let's go ahead and see one of my favorite examples of this. So system.out.println, and this surprises even experienced programmers. So it's going to be very surprising to you the first time you see it. And of course, I'm not going to give you the full information of why it works, because we'd have to dig down into the internal of how doubles are stored in a computer, and I don't really want to do that. But 0 plus 1 plus 0 plus 0.2, so 0.1, 0.2, right? In any sane world, that's 0.3, right? Let's see what Java says it is. So it's 0.3 and very tiny amount of change over here, right? What's going on here? Well, it's the same problem I was just talking about with 2 divided by 3. The issue is that we just don't have enough space to store all of the values. We don't have enough space basically we don't have a way of properly encoding this value in a binary system, right? Because it's all running underneath the system in binary. So this combination is just one of those values that just doesn't properly get encoded. And this isn't, and that's not the full story, but it's just simply a word of warning. It's not really going to affect you too much in this class, but every single programming language that uses doubles deals with it in the same way, right? It's just, so it doesn't matter what programming language you are in. It works the same way in C. Sometimes it's happened. It should never really pop up in this class. Aside from the fact that I just told you that it exists. Okay, so we learned about doubles, and we learned about, so we learned about doubles, we learned about integers. What other types can we store in Java? Well, the other important thing are what we call characters, which are given the unassuming name of char for short, or char for short. Now, these things are, under the hood, they're just integers, okay? But what they do is that they represent single characters, okay? Okay. It's a single character. So if I ask it to print C, print character C out, print line, it will print out A, because that's what I said storing it. Notice the single quotation marks as opposed to the 2 quotation marks. Characters get single quotation marks. I can't put more than one thing in there. A character is just a single symbol, right? The symbol that represents A, the symbol that represents B. Okay? The symbol that represents B plus 3. What? B plus 3? That's valid. A, B, C, D, E. Three characters after. These are just numbers underneath here, right? This is what I'm saying. So these values are just numbers underneath the hood, which will make cryptography, by the way, very, very easy for us to do. Much easier for us to, because we can translate numbers to integers. Actually, the entire idea of how do we encode things, how do we encode letters into numbers, because remember, your computer only understands numbers. It's a very hard problem. that basically was only kind of sort of solved, not too long ago after much headbanging against the walls. What we use is something called Ascii. Well, not really, but I'm lying to you. But right now, because we're in an American-centric university, in the United States, well, not so much American-centric as English-centric, that we found out, hey, we can basically encode pretty much everything we need to in English if we just use 7 bits. Okay? And then all those other countries that have weird things like umlauts and stuff like that, they can, for their own independent country, they can have, they can use that 8th bit. They can use all 8 bits to encode all those extra stuff. So we can use the first 100. So all the Anglophile countries, we can use the first 128 bits, called Ascii, and every other country like Hungary or Bulgaria or Greece, or Germany, who they need umlauts and little weird symbols on top of their symbols. They can use every country can have their own independent encoding for those other 128 bits, not bits, but numbers, symbols. So we can encode using Ascii 256 characters. Anybody see a problem with that? If you're coming from an Asian country, you should probably see a huge problem with that.
Some languages have more than 250.
Yeah, some have way more than 256. How many characters are there in Chinese?
So that's how I don't know.
It's standard in Mandarin, but estimate. Give me an estimate.
12,000.
What?
12,000.
12,000. Okay, that's more. That's some. And I have no idea if you're right or not, but that's way more than 256. So how that works is basically something we'll get into later in the semester, but it is a pain in the butt, or it was a pain in the butt for a while for me to get an email from somebody in another country and for it to be properly displayed on my screen. That was such a huge pain in the butt, notwithstanding the difficulty of actually getting email, a couple decades ago. So, but for right now, we can deal, because we're dealing with, again, in an Anglophile country, we can just ignore all that for right now and pretend that we're dealing in Ascii still, which is basically that every single symbol is represented by a very easy number. So, for instance, 92, the number 92 is a character, right? And so let's figure out what the number 92 represents. So it represents the backslash. 97 represents A. So 98 is B, 99 is C, 100, and these are just symbols in binary. You don't really have to think about that unless you're dealing with cryptography, so that's fine. So, but every single character is given a representation. So 4, right? The character 4 has an encoding in it. And this is just so we can represent text. Now, we don't actually now in Java, unlike in C, we aren't actually going to work with characters too much. Because dealing with one character at a time, you can imagine that that's super tedious, right? Instead, we deal with something called strings, and we'll get into that in a second. But a character, a double, an integer, these are all what we call primitives. And they're, the programming environment basically just denotes that they're, them as keywords. And what that means is Java is what we call an object-oriented programming language, as I mentioned in the first lecture. And essentially, if it's not a primitive, it's something called an object, which is which is built using these primitives. But these integers, these characters, these longs, these doubles, they are used to build everything. There's only one more other primitive I haven't introduced you to, and we're going to get better use of it later in Chapter 3, so I'll just briefly mention it here. And if you're taking Math Concepts 1, right? So you're probably getting exposed to this thing, if not now, then very soon, and that's the Boolean value, named after George Boole. And these hold only only 2 different values, true or false. Okay, that's all these will hold, true or false, and they're used for figuring out logical operations. We're gonna, and you'll see them a lot of times in less than or greater than kind of expressions, but right now we're just gonna completely ignore they exist, right? Until we're gonna ignore they exist until about Monday. So, okay, great. Now on to strings. So strings are not primitives. And so let's talk about things that aren't primitives. So we're going to talk about two things that aren't primitives. We're going to talk about strings and scanner. So scanner, right, was something you probably picked up without too much understanding of what it was back when we were dealing with, our first homework. So let's go ahead and I'll save this class, and I think we need to move on to a new sort of clean canvas. So string example. So strings aren't what we call primitives. They're objects, meaning they're more powerful than our standard primitive. I mean, that's a lie. There's actually way more intricacy in what an object is. But for right now, just think of them as really powerful things built using primitives, which is the truth from a certain point of view. Okay. So here we go. Public static void main string args, right? So there's the magic word. And notice that I say string over here. So what is a string? Well, we've been dealing with a string since lesson 1. And a string is just a bunch of characters just glued together between quotation marks, right? Now, strings are cool. They can be as long as you want them to be, right? I only stopped typing because I got bored. So strings can be ridiculously long. Okay, if I open up a file that's 500 that's maybe 50 megabytes long, that's just text, like the complete works of Shakespeare, I could treat that entire book, the entire complete works of Shakespeare, as a single string if I wanted to. Right? Strings can be unlimited length. They're unlimited number of characters just glued together. And because strings are so useful, so ubiquitous in programming, that Java does something pretty unprecedented, which is that it allows us to treat strings as primitives, so we don't have to learn anything extra to learn how to use them. So string words is equal to hello, have some words. Right? I just build it like I would a character, except it's going to use quotation marks. The only difference is that basically, notice it's got a capital S. And that's to denote that it's built using an object rather than a primitive. Technically, it's a class, but again, we're trying to keep this as simple as possible to begin with, and then we can start working on the proper vocabulary. So it's the type of this is string. Now, again, notice how I've been writing my variables. I can make my been pretty trash, actually pretty bad with naming my variables. I called it int x, long L, double D, character C. Only when I was actually working on a problem did I actually do something correct, which is that use, an actual word, radius, to describe this. Radius rather than R, so it would be easier to read and understand. Pi rather than P, This is the opposite approach to mathematicians who think basically if you use a variable, it should probably be a single letter, preferably from a dead alphabet. So, So, string words, system.out.println words. So Java is what we call case sensitive, by the way, when it comes to variables. Hello, have some words. So if I make this capital W over here, it's not going to work. It's going to say, hey, you asked me to find the variable capital W words. I don't see it anywhere, right? So this is what we call case sensitive. So case sensitive means that basically I need to have lowercase. If I say lowercase, all lowercases over here, they have to be all lowercase. Now, there's also a convention for naming your variables, and I've been following it, which is that basically, except for pi, which is an exception we'll get to later, which is that if it's a variable, I should keep it all lowercase. So notice how I kept it, I didn't call it string capital W words, it was all lowercase words. And it certainly wasn't, that SpongeBob SquarePants meme of words. So, it was just all lowercase words. Now, what we do in Java is that if we wanted to, make this into, if I wanted my variable name to be multiple words, like my words, I do what's called Camel Cases, which is basically anytime I have a new words in my variable name, like this, variable of name for some words, I create a I make every letter basically that starts a new word a capital letter. Why is it called camel case? Well, because it's got humps in it. It's a really bad joke. Okay. So just like camels have humps, the capital letters here are treated as humps. So, but we can make our variable names pretty much as long as we want. The other way to do it is to use underscores. So you just keep it all lowercase, but instead you separate stuff via underscore. Java prefers it to be done with camel case. The way of doing it in C is to use underscores to separate your characters. Which way is the correct way? Consistency is the correct way. It doesn't matter. I don't care. In Java, technically the correct way is to use camel case. But if you prefer doing it this way, then do it this way. What is correct is consistent, meaning so long as you use the same type of casing, camel case or underscores, so long as you use the same type throughout the entire program, it doesn't matter. Why don't you want to mix and match? Because you'll forget later on which you were using, right? Because your programs eventually become very long. All right. Now, strings are pretty cool. They have a special... Now, you can't subtract strings from one another. I can't subtract words from this in Java. And I certainly can't multiply, right, or divide. But I can add, because the addition operation does make sense. I can add strings together. And what that does, it's actually not the addition operator. We just use the addition symbol for it. When we're dealing with strings, this addition operator is called concatenation, which is really a big and fancy way of saying, let's glue these two strings together, right? And it leads to some interesting things. So, string nums is equal to So let's go ahead and say nums plus 1. Now here we have another instance of type conversion, which you've seen earlier, which I showed earlier, which is basically, right, so I mentioned that basically ints have, they have a limited number of space of the stuff they can store, right? And doubles also, even though it's technically not that, even though those numbers can be very big, there's technically a length for how big doubles can be. But strings, they can be as long as we want them to be. They're bigger than everything, right? So anything that we add to a string like this automatically gets converted to a string. So here is not going to be 11. It's going to be, 10 plus 1 converted to a string. So it's going to be 101 because this 1 gets converted to that. And we get 101. By the way, that's also almost always a test question worth 1 point on my exam. Basically, what is this value? And pretty much everybody gets it right. A lot of questions on my test of these kinds of questions, almost everybody can get right. Why do I ask them? Because occasionally some people get them wrong. 1001. Right. So this is, but strings are pretty straightforward. We use them to get text. Now, mind you, the computer just doing this isn't that interesting, right? It's just spitting up stuff out to you isn't that interesting. It makes for very boring programs. What we'd like is some interactivity. And that's where scanner comes in, which is like a string, it is an object. Okay? But because we don't have to use it so often, it requires us to go through a couple steps. The first thing I'm going to call it is I'm going to create a scanner variable. Right? Now, you can... I skipped over this, but I can just declare a variable to begin with. I can go like int x, and I can leave it lying around for later for when I want it, right? I can do this. Int x is equal to int x, so that just says I'm making space. Make space for x, essentially. saying, I'd like there's a variable X, I'm going to use it later. But the vast majority of time when you create something, you probably know what you want, right? You know what you want, so you just combine it into one statement. Same thing with here. So the first thing is that it's giving me an error here. So scanner cannot be resolved into a type, meaning it doesn't know what a scanner is. Of course, I've got this little light bulb here that might be hard to see on your screen, but it's simply saying that, well, how do we solve that? Oh, the first thing we need to do is import it. Now, importing is basically that there's a lot of Java code that already exists. I can do this, I think. Yeah, that's great. So, awesome. So there's a lot of Java code that already exists for us. So let's look at like the Java API. Oh, come on. Don't make me fight with you. Oh, it's making me fight with it. Okay, so give me a second. There we go. Okay, so this is all stuff that the developers of Java have all written. String and scanner are just two of the things that are in here. So, obviously, you have to know all these things by the end of your bachelor's degree. Obviously, right? Hell no. No, I don't even know like half the things in here. Not even a quarter of the things in here. I mean, these are just tools that that basically that exist for you to that are already written in Java. And this is a lot of stuff. Okay? And the idea is that basically not every program is going to need to know all the details about the Gregorian calendar. Really? Okay, we're going to just, sorry, give me. Stop the scene switcher. There we go. Okay, we don't need to know, not every program needs to know how the Gregorian calendar works. We don't need to lay out stuff in a grid for in every program. We don't need windows for every program. We don't need so a lot of times programs just run in the console, especially in this class. We're going to learn how to do some GUI stuff. That's something new I'm going to try this semester. I'm going to introduce some GUI stuff. So a lot of stuff we don't need in a program. So Java just simply loads up the basics for the most part. String gets loaded in because every program pretty much needs a string. It's super rare that you don't need strings. What else do you need? Well, it's very common, and it comes at a very little cost to add in what we call the math class, which we'll learn, which has some very useful things like, you know, it has stuff like, you know, the actual value of pi stored in there. So it's a bunch of little operations that are just very useful because that we don't need to import. Everything else pretty much we need to import. Just because if we import it, that's just going to add to the size of the program we are going to be sending out to people. And we'd really like it to send it out. When we send it out, we'd like it to be as small as possible so it gets downloaded as quickly as possible, right? So scanner, that's why you have to import it, because it's not every program needs to you know, have user input through the scanner. But it's super powerful. Later we're going to see how we can just read an entire website with scanner. Not now. That comes at the later semester. But the first thing we have to do is create a scanner. And this, again, is, I'm sorry, more black magic, but I guarantee basically a lot of the stuff that we're doing, and you'll understand at the end of the class. To create a scanner, we use the magic phrase, new scanner. Okay, now, we can't just leave it like this, though. Normally, like, for a lot of stuff, this is just fine when we're creating stuff, like using this magical new phrase, which simply says, create a new of whatever is over here. It's asking me what the heck I'd like to scan. So I have the options of doing stuff like looking at a file, some file I'd like to scan maybe. But the most of the time in this class, we're going to be scanning, system.in, right? We're printing out via system.out. System.in is something we'd like to scan. What is that? That's us hitting the keyboard. Okay. So I'd like to scan system.in, and I'm using KB over here, but let's go ahead and be a bit more, denoted over here with keyboard. So we're going to read in from the keyboard, right? So this object's going to represent the keyboard. And that's what an object is. It's modeling something in the real world. So strings model, you know, a bunch of text. Scanner models, you know, something that we can scan for data. Okay? So what's cool is that we can do stuff like this. System. So let's go and start with the most basic program, which we'll call with scanner, which is what we call echo. Echo named after the I think the Greek, what was she, a nymph in Greek mythology who fell in love with Narcissus. That was it. So echo program. Please enter something, right? Always give your user, you know, instructions on what to do. So the way we use scanner like this is to ask them for something. So keyboard dot. So let's go ahead and what we can do is that we can basically read. This is the most basic thing we can do, which is we can read a line of text from the user. So keyboard dot next line. Okay, next line. What that will do is that will read basically a bunch of text until it finds me hitting the enter key. Okay, something like there's other stuff you can do, but this one reads that. And what we want to do is we want to do this. String s is equal to keyboard.nextLine. So remember what this says. This says take the thing. What the equal sign says over here. It says take the thing on the right and store it on the left. Well, keyboard.nextLine, that's like a command, right? Well, remember, anything over here on the left, on the right, is what we call an expression, right? And expressions need to be evaluated. So we evaluate keyboard.nextLine and put its result in string s. Does that make sense to everybody? We're going to evaluate this and put it in string s. Okay, so again, what we're doing is we're evaluating, creating a new string, a scanner, and we're storing the new scanner in keyboard. We evaluate this and do this command. We do this command. So it's always evaluating. You know, it's not, you know, not always be closing. It's always be evaluating. So we do this, and now we can do this. System.out.println. And let's give this a better name than s, right? Input. You entered input. And let's say, so we don't want to just put input over here because it would just literally print out input, right? Instead, we want to say glue this string together with the what's ever stored in input. So let's run our echo program. Echo program. Please enter something. Something, because, you know, I'm kind of literal like that. You entered something. So fairly straightforward, right? All it's doing is just printing out what I put in. That's the most basic use of scanner. So let's go ahead and copy paste this. Okay? So there's a lot of lessons that we still have to learn with regards to variables, and we're just going to learn them as they come up. Uh-oh, I've got an error. An error we haven't seen before. Duplicate local variable, what? I should be able to use variables more than once, and you can. But when you put a type like this up here, this is basically saying, remember, so this is two commands, as I alluded to. Create an integer x, right? And set x to 5, right? That's what this is. That's two commands just baked into one, okay? But if I wanted, so if I said this again, int x, Java's going to look at me funny. It says, you already created x. What are you talking about? Create a different, something else, right? You just want to reuse it, right? And that's exactly what's going on over here. When we say string input is equal to this, we're saying take this evaluate this and store it in something new, a new string called input. So here we're going to put And we can always just separate this by spaces too. So here I say, instead of saying string input, I say, because the input's already been created, use this. So you can't create a variable more than once. But I can reuse the variable as many times as I want. Okay. So, foo. You entered foo. Please enter something else. Bar. You now entered bar. Right? So we've created, so what did we learn today? Okay? And obviously we don't have time for our quiz today, so that's going to be pushed back into the next class, so into the next lab. It's fine. Because I wanted to get further, I figured actually it was more valuable to do this. So in lab, you know, you can do that on, you'll need a computer, but fortunately in lab, you've got a computer in front of you. We learned about integers. We learned about doubles. We learned about the various types of data. We learned a bit about variables, and we learned a bit about all this stuff over here. We learned how to create a new variable. Well, kind of. I've mentioned it in a slide at the end. Yes?
So we put like both of their inputs together, like you entered foo bar, like you know.
Okay. We could glue them together. And I'll get into that later, because there's a bunch of other operations that we can do, like self-modification of a variable is one thing we can do, or updating a variable. But I don't want to get into that right now because it's not relevant for what we need. So your homework on Friday will be something called it'll be a two-part homework. Your first one is I'm going to give you, for the first part, it's going to be something called you're going to be solving for something called the basal metabolic rate, which is the amount of calories you consume just by being alive. It's actually the vast majority of your calories that you consume just by, staying alive. So you're going to calculate the basal metabolic rate for, you're going to ask the user to enter their age, their weight, and their height, and use that to calculate what, and it's different equations if you're a man or a woman, and you'll calculate both of them. And then you're going to figure out how many bars of chocolate do you need to consume in order to stay alive if you don't do anything else. So basically, how many bars of chocolate does it take to maintain your basal metabolic rate? So that's your first homework on Friday. Your second homework is that, and they're both worth 50% of your homework grade for this week, is that I'm going to give you a program that's got a bunch of errors in it. Basic errors that you've all learned about so far, and I'd like you to please fix them.
And what's the quiz going to be on?
The quiz will be on stuff from Chapter 1. So basically, nothing more exciting than writing a Hello World program will be on it. So the first quiz will be on that. Next week, there will be a quiz on expressions and evaluating expressions in PEMDAS and stuff like that. But, we'll get to